Hi, so today's lesson is going to be regarding Chapter 11, which is all about alkynes and synthesis. So here's a brief outline of this chapter. We'll discuss what alkynes are, how to name them, and we're also going to take a look at some of the physical and chemical properties of alkynes, how to prepare them, what kind of chemical reactions they undergo, such as addition of hydrogen halides, addition of halogen, addition of water, hydroboration-oxidation, and finally reaction of acetylide anions. So alkynes are unsaturated hydrocarbons containing a carbon-carbon triple bond. And you already know that a triple bond contains one sigma bond and two pi bonds. And because of this, the triple bond introduces 2 degrees of unsaturation, coming from the presence of 2 pi bonds. An alkyne has the general molecular formula CnH2n-2, giving it 4 fewer hydrogens than the maximum possible for the number of carbons present. And that's why alkynes are considered unsaturated hydrocarbons. Alkynes can be classified into 2 types, terminal alkyne and internal alkyne. A terminal alkyne has the triple bond at the end of the carbon chain, so that one hydrogen atom is directly bonded to a carbon atom involved in the triple bond. On the other hand, an internal alkyne has a carbon atom bonded to each carbon atom involved in the triple bond. So here you can see that in a terminal alkyne, the triple bond is at the end of the carbon chain, in which one of the carbon atoms involved in the triple bond is bonded to a hydrogen atom, and the other carbon atom involved in the triple bond is bonded to a carbon atom. On the other hand, in an internal alkyne, the triple bond is within the carbon chain, in which both carbon atoms involved in the triple bond are bonded to one other carbon atom. So here you can see that we have an acetylene molecule, which is the simplest alkyne molecule, consisting of 2 carbon atoms that are triple bonded to one another. And you already know that the triple bond contains a sigma bond and 2 pi bonds, as shown here. And because of this, each carbon atom in the triple bond is sp hybridized, having linear geometry with 180-degree bond angles. And due to the hybridization of the carbon atoms, the carbon-to-hydrogen bond in alkynes is considered more acidic than the carbon-to-hydrogen bond in alkenes or alkanes. The energy of the second pi bond in an alkyne can easily be estimated by taking the difference in the bond dissociation energies between an acetylene molecule and ethylene molecule. So here we have the bond dissociation energies for acetylene and ethylene. Taking the difference between them, we get 202 kilojoules per mole, which is the estimated energy for the second pi bond in an alkyne molecule. Both pi bonds in the triple bond are easily broken in a lot of chemical reactions because they are relatively weaker compared to sigma bonds. As a result, alkynes undergo many addition reactions. Here's practice problem number 1. So here we have the structure of nepheliocyne B. Question A here, label the most acidic hydrogen atom. So for part A, the most acidic hydrogen atom is this one right here, which is part of a carboxylic acid group or carboxyl group. And for part B here, it says which carbon-carbon sigma bond is the shortest. So when it comes to the sigma bond, the length of a sigma bond, we have to look at the hybridization of the carbon atoms. And so the higher the percent S character, the shorter the sigma bond is. And so when you look at these triple bonds, we have 1, 2, 3, 4 triple bonds here. And these triple bonds contain one sigma bond. And the sigma bond comes from the carbon-carbon sp hybridized carbons. So they have, each of these carbon atoms contain 50% S character. And so that means that they would be the shortest bonds here. And for part C here, it says how many degrees of unsaturation does this compound contain? And so when we're counting the total number of degrees of unsaturation, all we have to do is count the total number of pi bonds and number of rings. But since we don't have any rings here, we only have to take care of number of pi bonds. So triple bonds contain 2 pi bonds, and then double bonds contain 1 pi bond. So here we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So we have a total of 13 pi bonds, which indicate that we have 13 degrees of unsaturation. And for part D, it says how many bonds are formed from sp hybridized carbon to sp3 hybridized carbon atom. So here we only have a few sp hybridized carbon atoms that are bonded to an sp3 hybridized carbon. So here, for instance, we have an sp hybridized carbon bonded to an sp3 hybridized carbon atom. So this is one bond here. So we can label that. That's one bond. And then here's another sp hybridized carbon bonded to an sp3 hybridized carbon atom. This one right here is also an sp to sp3 bond. Same thing with this one right here, and this one right here. So we have a total of 1, 2, 3, 4, 5, and 6. So we have a total of 6 sp hybridized carbon bonded to an sp3 hybridized carbon. And for part E here, it says label each triple bond as internal or terminal. So for the first triple bond here, this is a terminal alkyne because it's at the end of the carbon chain. The second, third, and fourth triple bonds are all internal alkynes. So how do we name alkynes? Alkynes are named using the same IUPAC system that we use in naming alkanes and alkenes. The only difference is we're changing the suffix into YNE. And so we're going to choose the longest continuous chain that contains both atoms of the triple bond and then number the chain to give the triple bond the lower number, followed by naming and numbering the substituents. So alkynes containing 2 triple bonds are named as diynes. Those containing 3 are named as triynes, and so on and so forth. Compounds containing a double bond and a triple bond are named as enynes because it's a combination of an alkene and an alkyne. The chain is then numbered to give the first site of unsaturation, either a carbon-carbon double bond or a carbon-carbon triple bond, the lower number. Here's a few examples. So for the first example here, we have 2,5-dimethyl hept 3-ine. So when you count the longest carbon chain here, the longest continuous carbon chain, it contains 7 carbon atoms. So we have 1, 2, 3, 4, 5, 6, and 7. And so we have a heptane. And because this is a triple bond here, we have a heptyne. And then the triple bond is on the third carbon atom. And so we're going to call this hept 3-ine. And then, of course, we have 2 methyl groups, one that's bonded in the second carbon atom and another one on the 5th carbon atom. So here we have 2,5-dimethyl hept 3-ine. And for the second one here, we have 1-ethanyl 2-isopropyl cyclohexane. And so since we have a cyclic ring, we're going to name this as a cyclohexane. And this group right here, this substituent, is known as ethanyl because it contains 2 carbon atoms and they are triple bonded. So this is called an ethanyl group. And this one right here is an isopropyl group. And so we want the triple bond to have the lower number. So it's bonded to this carbon atom labeled 1. And so we have 1-ethanyl 2-isopropyl cyclohexane. And for the third alkyne here, you can see that the longest carbon chain contains 1, 2, 3, 4, 5, and 6. So this is going to be a hexane based. And since we have 2 triple bonds here, this is going to be a diene. And so the first triple bond is on the first carbon atom, and the second triple bond is on the third carbon atom. So in this case, we can name it hexa 1,3-diene. And for the last one here, you can see that the longest carbon chain contains 6 carbon atoms. We have 1, 2, 3, 4, 5, and 6. And you can see that this contains a triple bond and a double bond. And so we're going to call this an enyne because it's an alkene and an alkyne. And so we're going to label the carbon atoms so that the triple bond is labeled 1. It has a lower number. And so we have a triple bond which is on the first carbon atom, and then the double bond on the fourth carbon atom, and then a methyl group on the 5th carbon atom. And so when naming this molecule, we have 5-methyl hex 4-ene 1-ine. So again, that's 5-methyl hex 4-ene 1-ine. Here's another example. Give the IUPAC name for the following alkyne. So the first thing that you want to do here is to determine the longest carbon chain. And so the longest carbon chain here contains 8 carbon atoms. 1, 2, 3, 4, 5, 6, 7, and 8. And then you're going to label the carbon atoms so that the triple bond gets the lowest number. So in this case, we have 1, 2, 3. We're going to label them from left to right. And because it contains 8 carbon atoms, the longest chain contains 8 carbon atoms, this is going to be an octane based. And because we have a triple bond, this is going to be an octyne, where the triple bond is on the 3rd carbon atom. So this is going to be oct3-yne. And then finally, we have a dimethyl group on the 6th carbon atom. And so this is going to be 6,6-dimethyl. So in this case, we have 6,6-dimethyl oct3-yne. So here's practice problem number 2. Give the IUPAC name for each compound. So for the first compound here, the longest carbon chain contains 7 carbon atoms. Starting from here, containing the triple bond, so we have 1, 2, 3, 4, 5, 6, 7. So this is going to be a heptane based. And since we have the triple bond on the first carbon atom, this is going to be hept1-yne. Hept1-yne. And then looking at the substituents on the 4th carbon atom, we have 1, 2, 3 carbon atoms. So it's going to be a propyl group. And since we have 2 of them, it's going to be a dipropyl. So this is 4,4-dipropyl hept1-yne. For the second compound here, you can see that the longest carbon chain contains 8 carbon atoms. And we have to label the carbon atoms so that the triple bond has the lowest number. So in this case, we're labeling the carbon atoms from left to right. So that's 1, 2, 3, 4, 5, 6, 7, and 8. And since we have the longest chain containing 8 carbon atoms, this is going to be an octane based. And then the triple bond is on the 3rd carbon atom. So this is going to be oct3-yne. So we have oct3-yne. And then we have a methyl group on the 6th carbon atom, another methyl group on the 5th carbon atom, and then a chloro group on the 5th carbon atom. Since chloro comes first before methyl alphabetically, it's going to be 5-chloro, and then 5,6-dimethyl. And so the name of this compound is 5-chloro-5,6-dimethyl oct3-yne. And for the third compound here, you can see that the longest carbon chain contains 10 carbon atoms. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a decane based. And because this compound contains a double bond and a triple bond, we're going to name this as an enyne. And we're going to label the carbon atoms from left to right so that the double bond or the triple bond gets the lower number. And since the double bond gets the lower number here, we're labeling it from left to right. And so the double bond is labeled 1, and then the triple bond labeled 5. And then the other substituents here, we have an ethyl group on the 4th carbon atom, and then a dimethyl group on the 7th carbon atom. And so again, as an enyne, this would be dec1-ene 5-yne. So again, that's dec1-ene 5-yne. And then the ethyl comes first before the methyl. And so this is going to be 4-ethyl 7,7-dimethyl dec1-ene 5-yne. And for the last molecule here, we have the longest chain containing a total of 8 carbon atoms. And this consists of 2 triple bonds. So this is going to be a diyne. And again, we're labeling the carbon atoms from left to right so that the first triple bond has the lower number. So this is 1, 2, 3, 4, 5, 6, 7, and 8. And because the longest chain contains 8 carbon atoms, we're going to have an octadiene. And again, that's octa-1,5-diene. And then regarding the substituent, we have an isopropyl group on the 3rd carbon atom. So we have 3 isopropyl octa-1,5-diene. And here's practice problem number 3. Give the structure corresponding to each of the following names. Trans-2-ethynyl cyclopentanol. So for the first one here, the first thing that you want to do is to draw the cyclopentanol. So this is a cyclic ring containing 5 carbon atoms and a hydroxy group. So you can see we have a cyclic ring with 5 carbon atoms and then a hydroxy group. And then on the 2nd carbon atom, so this counts as the 1st carbon atom, and then this could be a 2nd carbon atom or this one right here. So let's pick this one as the 2nd carbon atom. And trans to the hydroxy group is the ethynyl group, which is a triple bond. 2 carbon atoms that are triple bonded. So this is trans-2-ethynyl cyclopentanol. And for the second one here, we have 4-tert-butyl-dec-5-ine. So again, we have 4-tert-butyl-dec-5-ine. And so the first thing that I would want to do here is to draw the triple bond. So the longest chain contains 10 carbon atoms because this is a decane based. And then on the 5th carbon atom, we have a triple bond. So the 5th carbon atom is triple bonded to the 6th carbon atom. So here it is. We have 2 carbon atoms that are triple bonded, labeled carbon 5 and carbon 6. And then we're going to go ahead and connect the rest of the carbon atoms in the chain, which contains a total of 10 carbon atoms. So here's 1 through 7, and then the rest all the way to 10. And then it says over here that we have a tert-butyl group that's bonded to the 4th carbon atom. Here's the tert-butyl group, and so this is the structure for 4-tert-butyl-dec-5-ine. And finally, for part C, we have 3,3,5-trimethylcyclononine. And again, the very first thing that I would want to do here is to draw the triple bond. And we have a cyclononine, so that means that we have a cyclic ring containing a total of 9 carbon atoms. So here's the triple bond. So we have 2 carbon atoms that are triple bonded to one another. And then we're going to connect the rest of the carbon chains. So we're going to connect the rest of the carbon atoms in which it forms a cyclic ring. So again, that's a total of 9 carbon atoms. And so we're going to label the carbon atoms. You can start from up top. So again, the triple bond gets the highest priority here. So we can label this 1, 2, 3, 4, 5, 6 clockwise. All right. And then we have methyl groups, 2 methyl groups on carbon number 3, and then 1 methyl group on the 5th carbon, as shown here. So this is the structure for 3,3,5-trimethylcyclononine. And in terms of physical properties, alkynes actually have very similar properties as the other hydrocarbons, alkanes and alkenes. And so they have low melting points, they have low boiling points, and the melting point and boiling point increase as the number of carbons increases. And finally, alkynes are soluble in organic solvents, but insoluble in water. And again, the reason why is because they are nonpolar compounds. So one example of an alkyne is ethyne. And this is actually the simplest alkyne because it only contains 2 carbon atoms that are triple bonded to one another. Its more common name is acetylene. This 2 carbon alkyl group, which is derived from acetylene, is known as ethynyl group. Acetylene is a colorless gas that burns in oxygen to form carbon dioxide gas and water vapor. And this is a combustion type of reaction. This combustion releases a huge amount of energy per mole of product formed than any other hydrocarbons. And the reason why is because a triple bond contains a sigma bond and 2 pi bonds. And so because it releases a huge amount of energy, its flame is extremely hot, and it's often used in welding. In one of the previous chapters, you learned that alkynes can actually be prepared via elimination reactions. So if you have a geminal dihalide or a vicinal dihalide undergoing two successive E2 elimination reactions will result in the formation of an alkyne. So here we have a geminal dichloride reacting with a strong base. And after two successive E2 elimination reactions, what we get is an alkyne, in which the triple bond is between the second carbon atom and the third carbon atom. So alkynes can also be prepared from alkenes via a two-step process. The first step is halogenation of the alkene, as shown here. So halogenation of the alkene results in the formation of a vicinal dihalide, followed by double dehydrohalogenation, which then results in the formation of the alkyne. So here's practice problem number 5. Convert each compound to hex 1-ine. So for the first compound here, you can see that we have a vicinal dihalide, and so we can convert this into an alkyne by reacting this via two successive E2 elimination reactions, or dehydrohalogenation reactions. And so the first E2 elimination reaction here reacts it with a strong base, and so this gets rid of a hydrogen on an adjacent carbon atom, which is this one right here, and also a bromine atom in the process. And so what we have is this product right here, and then the second E2 elimination reaction would result in the elimination of this bromine atom and an adjacent hydrogen atom. And so what we have is the alkyne hex 1-ine. And for part B here, you can see that we have an alkene, and so the first step here is bromination or chlorination, and I'm using bromine gas here, and so this is going to turn the alkene into geminal dihalide or geminal dibromide, as shown here. And then now we can react this this geminal dibromide via two successive E2 elimination reactions. And so what we get is the same alkyne, hex 1-ine. And for the last one here, we have a primary alcohol. And so in order to convert this into an alkyne, the first thing that we want to do here is to convert this alcohol into an alkene. And so we're going to dehydrate this alcohol using strong acids, such as sulfuric acid. So we're going to dehydrate this alcohol using sulfuric acid. And this basically turns the bad leaving group, which is the hydroxyl group, into a good leaving group, which is water. And so now what you have is the proton transfer reaction, which cleaves the hydrogen that's bonded to this carbon atom right here. And so what we have is a formation of the double bond, the alkene. And then after the formation of the alkene, we can now react it with bromine with Br2. And so what we get is the formation of a geminal dihalide followed by two successive E2 elimination reactions. And this results in formation of hex 1-ine. So alkynes can also undergo addition reactions because they contain pi bonds similar to alkenes. And so alkynes can undergo two sequential addition reactions as shown down here. So we have an alkyne containing two weak pi bonds, and the first step results in the cleavage of the first pi bond and the formation of two sigma bonds via the addition of the elements X and Y. And the second step results in the cleavage of the second pi bond and also results in formation of two additional sigma bonds for a total of 4. So here's the electrostatic potential map of the molecule acetylene, which is the simplest alkyne molecule. Here you can see that most of the molecule's electrons are located at the center of the molecule, where the triple bond is. And so this exposed electron density makes a triple bond nucleophilic, similar to a double bond in alkenes. And so because alkynes are acting as nucleophiles, they react with electrophiles. Alkynes can undergo several different types of addition reactions, similar to the alkenes. For example, we have hydrohalogenation reaction, which is the addition of hydrogen halides. Halogenation reaction, which is the addition of halogen atoms. Hydration reaction, which is the addition of water. and hydroboration reaction or hydroboration-oxidation reaction, which is also the addition of water. In each addition, both pi bonds of the triple bond are broken, and 4 new bonds are formed. In this chapter, we're going to take a look at every single one of these reactions in a little bit more detail. In one of the earlier chapters, you learned that the hybridization of a carbon-to-hydrogen bond affects the acidity of a proton. For example, sp hybridized carbon-hydrogen bonds are more acidic than sp2 and sp3 hybridized carbon-hydrogen bonds. And so terminal alkynes can easily be deprotonated with a strong base in a Bronsted-Lowry acid-base reaction. And the resulting ion is known as acetylide ion. Here's an example. So we have a terminal alkyne in which the pKa is about 25. Any base with a conjugate acid that has a pKa greater than 25 will be able to deprotonate this hydrogen atom. And this results in the formation of the acetylide anion. The acetylide anion that was generated can now act as a strong nucleophile, reacting with a variety of electrophiles, and this results in the formation of a sigma bond. So here's a table that shows you a comparison of bases for alkyne deprotonation. So here you can see that both the amide and the hydride ions are strong enough to deprotonate an alkyne. On the other hand, both hydroxide and alkoxide ions are not strong enough to deprotonate an alkyne because their pKa values, or the pKa values of the conjugate acid, are less than 25. So here's practice problem number 6. Which bases can deprotonate acetylene? The pKa values of the conjugate acids are given in parentheses. So acetylene has a pKa of 25. And so any of these bases listed here with a pKa greater than 25 will be able to deprotonate acetylene. So I'm just going to circle the ones that are able to deprotonate acetylene here. So we have the first one, A, has a pKa of 40, so this should be able to deprotonate acetylene. And this one right here as well. And so the other two, B and D here, both have a pKa of less than 25, and so they are not able to deprotonate acetylene. So now let's take a look at the different types of addition reactions involving alkynes. The first one here is hydrohalogenation, which is the addition of a hydrogen halide to the chemical structure. Hydrohalogenation reactions of alkynes result in the addition of hydrogen halides to the chemical structure. So here we have an alkyne reacting with one equivalent of a hydrogen halide, and this results in formation of a vinyl halide, in which you can have an E isomer or a Z isomer. Reacting this vinyl halide with another equivalent of a hydrogen halide results in formation of a geminal dihalide. And so the reaction of an alkyne with two equivalents of a hydrogen halide results in a net formation of a geminal dihalide. The hydrohalogenation reaction of alkynes follows the Markovnikov's rule, which basically means that the halogen atom will bind to the more substituted carbon. In order to illustrate this rule, we have two different types of alkynes undergoing hydrohalogenation reaction. The first one is an internal alkyne, and the second one is a terminal alkyne. So first, let's take a look at the hydrohalogenation reaction involving terminal alkynes. So here you can see that the bromine atom binds to the more substituted carbon, as shown here. So what we have is a vinyl bromide, and reacting this vinyl bromide with another equivalent of a hydrogen bromide results in the formation of a geminal dihalide, which is also observed in the hydrohalogenation of internal alkynes, as shown here. And so this suggests that the hydrohalogenation reaction involving internal alkynes also follows Markovnikov's rule. So here's the reaction mechanism. The first step involves the alkyne acting as a nucleophile, attacking this electron-deficient hydrogen atom, which then results in the cleavage of the sigma bond between the hydrogen and the bromine atom. And the first step generates a carbocation, in which the positive charge is on the more substituted carbon. The second step is the nucleophilic attack by the bromide ion, and this results in the formation of a vinyl bromide. The third step is the second hydrohalogenation process, in which the alkene attacks this electron-deficient hydrogen atom, and this sigma bond is cleaved, which results in the formation of another carbocation. The fourth step is another nucleophilic attack by the bromide ion, which then results in the formation of a geminal dihalide. So here's practice problem number 7. Draw the organic products formed when each alkyne is treated with 2 equivalents of hydrogen bromide. So for the first one here, you can see that we have a terminal alkyne. So you would expect the bromine atoms to bond to this more substituted carbon atom, according to Markovnikov's rule. So let's take a look at the reaction mechanism. So for the first one, reacting this alkyne with the first equivalent of hydrogen bromide results in the nucleophilic attack by this alkyne, attacking this electrophilic hydrogen atom. And this results in the cleavage of the sigma bond between the hydrogen and the bromine atom. And this results in the formation of a carbocation, which is followed by the nucleophilic attack by the bromide ion. This attack results in the formation of a vinyl bromide. And reacting this with the second equivalent of hydrogen bromide results in the formation of a geminal dibromide, which is the final product. And for the second alkyne here, you can see that we have an internal alkyne. So that means that these 2 carbon atoms are equally substituted. And so that means that the bromine atoms can either bond to this carbon atom on the left or this carbon atom on the right. And so reacting this alkyne with 2 equivalents of hydrogen bromide results in the formation of a mixture of compounds in which you have the 2 bromine atoms bonded to this carbon atom right here on the left, as shown here, or the bromine atoms bonded to this carbon atom on the right, which is shown here. And for the last alkyne here, you can see that we have another terminal alkyne. So that means that the bromine atoms will bond to this more substituted carbon atom according to Markovnikov's rule. And so 2 bromine atoms will bind or form a bond with this carbon atom right here. And here's another practice problem. Draw additional resonance structures for each cation. So for the first cation here, you can see that we have a chlorine atom that's bonded to a carbocation. And so the chlorine atom can share one of its lone pairs of electrons with this carbon atom. So it's going to form a double bond, as shown here. And in that process, the chlorine atom will gain a positive charge. And for the second one here, you can see that we have a double bond next to the carbocation and also an oxygen atom with 2 lone pairs of electrons. And so the oxygen can share one of its lone pairs of electrons to form a double bond. Likewise, this double bond can resonate between these 2 carbon atoms, which forms a double bond between these 2 carbon atoms, leaving this carbon a positive charge. And for the final cation here, you can see that we have 2 nitrogen atoms adjacent to this carbon atom. And so they both contain a lone pair of electrons, which suggests that they can form a double bond with this carbon atom. So the first possibility is that you have this nitrogen atom double bonded to this carbon atom, leaving this nitrogen a positive charge, or a double bond between this nitrogen atom and this carbon, leaving a positive charge on this nitrogen. So now let's take a look at the second type of electrophilic addition reaction involving alkynes. It's called halogenation. And so we're adding halogen atoms onto the triple bond, or the 2 carbon atoms involved in the triple bond. So the halogenation reaction process in alkynes is actually very similar to the alkenes. So here you can see that we have an alkyne undergoing halogenation reaction. So this first electrophilic addition reaction results in the formation of a transdihalide, in which the 2 halogen atoms are on opposite sides. The second halogenation process of the transdihalide results in the formation of a tetrahalide. Here's an example. So we have an alkyne undergoing chlorination reaction, which is an electrophilic addition reaction, results in formation of a transdichloride. And reacting this with another round of halogenation reaction results in a formation of a tetrachloride. So here's practice problem number 9. Draw the products formed when hex triyne is treated with each reagent. So the first part here, it says 2 equivalents of bromine, and the second part 1 equivalent of chlorine. And so for the first one, Reacting this alkyne with two equivalents of bromine results in the formation of a tetrahalide compound, in which the bromine atoms are in transposition. And for the second part, since we're only reacting the alkyne with one equivalent of chlorine, this will result in formation of a trans dihalide, as shown here. Again, the two chlorine atoms are in transposition. And the third type of electrophilic addition reaction involving alkynes is hydration. So in this process, we're basically adding water into the chemical structure. So here you can see that in the hydration of alkynes, a strong acid or a salt containing mercury is used as a catalyst. And this results in formation of an enol and then ultimately into a ketone, which is the final product. So here's an example. We have an alkyne undergoing hydration reaction in the presence of a strong acid such as sulfuric acid or a mercury salt. And this results in formation of a not so stable enol, which then ultimately converts into a ketone, which is the final product. So how do we know whether to use sulfuric acid by itself as a catalyst or in combination with a mercury salt? Well, that will depend on the type of alkyne that you have. If you have an internal alkyne, as shown here, you only need a sulfuric acid as the catalyst, and this results in formation of the ketone. Otherwise, if you have a terminal alkyne, you would need an additional catalyst, such as the mercury salt, and this results in formation of a methyl ketone via Markovnikov addition. The hydration of alkynes involves this process known as tautomerization, which is essentially the conversion of enol into its more stable form, the ketone. By definition, tautomers are constitutional isomers that differ in the location of a double bond and a hydrogen atom. So here you can see that we have a pair of tautomers A and B. A is the enol form and B is the keto form. Remember that an enol is a compound containing a double bond and a hydroxy group, whereas a ketone contains a carbonyl group bonded to two carbon atoms. So again, tautomerization is the process of converting one tautomer into another, and this is catalyzed by both acid and base. And there's a lot of different types of tautomerizations. One in particular is the Keto-Enol Tautomerization, which is basically the conversion of an enol into the more stable form, which is ketone. So here you can see that A and B are a pair of tautomers because the position of the double bond is different, as well as the position of the hydrogen atom. In the enol form, you have a hydroxy group that's directly bonded to a double bond. In a keto tautomer, you have the carbonyl group and additional carbon to hydrogen bond. In terms of equilibrium, the formation of the ketone is favored, and that's because the carbon to oxygen bond is a lot stronger compared to a carbon-carbon double bond. And that's why in the hydration of alkynes, the alkyne is converted to a less stable enol form, which is ultimately converted into a keto form. So here's the reaction mechanism of a Keto-Enol Tautomerization in acid. So here we have an enol, and the first step of this tautomerization process is protonation. And this results in formation of a carbocation, which is then resonance stabilized, in which the oxygen atom bears a positive charge. The second step of this tautomerization process is deprotonation, and this results in formation of the ketone, the final product. So here's the overall reaction mechanism involving the hydration of an alkyne. The first part is the conversion of the alkyne into an enol, and then the second part is tautomerization, which is the conversion of an enol into the ketone. So again, the first part in the hydration process is the formation of the enol. So we have an alkyne, which is protonated, and this results in the formation of a vinyl carbocation. The second step involves the nucleophilic attack by water, followed by the third step, which is deprotonation, and this results in the formation of the enol. And the second step in the hydration process is tautomerization. So the enol is first protonated, which results in the formation of a carbocation. And this carbocation is resonance stabilized so that the oxygen atom now bears a positive charge. And the last step is deprotonation, and this results in formation of ketone, the final product. So here's an example. Draw the enol intermediate and the ketone product formed in the following reaction. So here you can see that we have a terminal alkyne, and so we're going to need an additional catalyst here, which is the mercury salt. And so the first thing that you would want to do here is to draw the enol intermediate, which is shown here. So when the terminal alkyne reacts with the acid, what you have is the enol intermediate, in which the hydrogen atom is bonded to the less substituted carbon, and then the hydroxy group to the more substituted carbon atom. And then the next step here is another reaction of the reaction between the enol and the acid. And so the enol here is acting as a nucleophile, attacking this electrophilic hydrogen atom, which results in the cleavage of the sigma bond between the hydrogen and the oxygen atom. And so what you have is the formation of the carbocation. And so you can see that based on the structure that there's going to be a resonance stabilization here. You have lone pairs of electrons on the oxygen, which can form a double bond between this carbon and the oxygen atom, as shown here. And so the final step is deprotonation of this hydrogen atom by a water molecule. And so the sigma bond breaks between the hydrogen and the oxygen atom, which results in the formation of the final product, which is the ketone. Here's practice problem number 11. Draw the keto tautomer of each enol. So for the first enol here, you can see that we have an alkene here, a double bond, and then a hydroxy group. So in order to draw the keto tautomer, all you have to do is switch the double bond and a single bond, and then move the hydrogen to the other side of the double bond. And so what we have here is a double bonded oxygen, and then the hydrogen will be moved bonded to this carbon atom right here, as shown here. So this is our keto tautomer. And then for the second one, we'll do the same thing. So we have a hydroxy group and a double bond right here. And so we're going to switch the double bond. So now you have a double bonded oxygen and then a hydrogen that's bonded to this adjacent carbon atom that was originally involved in the double bond. And so again, we have a double bonded oxygen, and then now the hydrogen atom will be moved over here. And so we have the keto tautomer. And for the third one, we're going to move again the double bond. We're going to switch them. We're going to have a double bonded oxygen, and then the hydrogen atom bonded to this adjacent carbon atom. And then finally over here, we have the hydroxy group and the double bond. And so we're going to have a double bonded oxygen, and then the hydrogen will be moved to this carbon right here. And here's practice problem number 12. Ignoring E and Z isomers, what two enols are formed when pen-2-yne is treated with water, sulfuric acid, and mercury salt? Draw the ketones formed from these enols after tautomerization. So the first thing that I would want to do here is to draw the structure of pen-2-yne. So here's the structure of pen-2-yne, and then we're going to react this with the reagent, such as water, sulfuric acid, and the other catalyst, which is mercury salt or mercury sulfate. And so what we get is a mixture of enols. So we're going to have two different enols here. The first enol, since we have an internal alkyne here, you can have the hydroxy group that's bonded to the third carbon atom, or the hydroxy group bonded to the second carbon atom. And so they're equally possible. And so these are the two enols that are formed from pen-2-yne. And so the next step here is to draw the ketones formed after tautomerization. So for the first one here, you can see that we're going to have a double bonded oxygen, and then the hydrogen will be moved and bonded to this second carbon atom, as shown here. All right, and for the second enol here, we're going to have a double bonded oxygen that's an oxygen that's double bonded to the second carbon atom, and then the hydrogen that's bonded to the third carbon atom, as shown here. So these are the two ketones that are formed after tautomerization. And here's practice problem number 13. Draw two different enol tautomers of 2-methyl cyclohexanone. And B, draw two constitutional isomers that are not tautomers but contain a carbon-carbon double bond and a hydroxy group. So for the first part here, whenever you're drawing two different enol tautomers of a compound, all you have to do is move the double bond to the two adjacent carbon atoms. So now you have these two carbon atoms that are double bonded, and then connect a hydrogen atom and bond it to this oxygen atom. So now you have a hydroxy group and a double bonded carbon atoms. So for the first one, here's the first tautomer, enol tautomer. And then the next one, you would have the double bond bonded to, or have the double bond on these two carbon atoms here. So these are the two different enol tautomers of the same compound. And for the second part, it says, draw two constitutional isomers that are not tautomers, but contain a carbon-carbon double bond and a hydroxy group. So all you have to do is move the double bond anywhere else that doesn't look anything like the enol tautomers. And so we can move the double bond onto these two carbon atoms right here, or anywhere else that doesn't look anything like the enol tautomers. And so here's the first one and the second one. So we have the double bond between these two carbon atoms, and the hydroxy group remains in the same position, or the double bond that's between these two carbon atoms here. So these two are two constitutional isomers that are not tautomers, but contain a double bond and a hydroxy group. And the last example of electrophilic addition reactions involving alkynes is Hydroboration-Oxidation reaction. So as the name of the reaction suggests, Hydroboration-Oxidation reaction involves two steps. The first step is hydroboration, followed by oxidation. So here we have an alkyne undergoing hydroboration reaction, and this results in the formation of an organoborane. This organoborane undergoes oxidation reaction in a basic hydrogen peroxide solution. And this reaction results in formation of enol, which then tautomerizes into a ketone. And so the overall result of this electrophilic addition reaction is the addition of water to a triple bond. So the hydroboration-oxidation reaction of internal alkynes is a little bit different compared to terminal alkynes. The internal alkyne forms a ketone, whereas the terminal alkyne forms an aldehyde. So this means that the borane is added to the less substituted carbon in an anti-Markovnikov fashion. So here you can see that we have an internal alkyne undergoing hydroboration-oxidation reaction, and this results in the formation of an enol and then gets tautomerized into a ketone. However, for a terminal alkyne, you can see that in the hydroboration-oxidation reaction, you get an enol in which the hydroxy group is bonded to the less substituted carbon atom, and this gets tautomerized into an aldehyde. So here's an example. Draw the product formed when butane is treated with each of the following sets of reagents. So here you can see that we have a terminal alkyne, and so reacting this with water in the presence of sulfuric acid and mercury sulfate as catalyst results in the formation of an enol, as shown here. And so you can see that the hydroxy group is bonded to the more substituted carbon atom, which is this atom on the left. And this enol gets tautomerized to form the final product, which is ketone. And ketone is the more stable product. And again, you can see that the carbonyl group is bonded to the second carbon atom on the left. Alright, however, if we were to react this via hydroboration-oxidation reaction, what we get is a completely different compound. And so here you can see that via hydroboration-oxidation reaction, the enol has the hydroxy group bonded to the less substituted carbon atom, which is the terminal carbon. And so the reason why is because of steric factors. And so boron is a large atom, and so it will bond to the less hindered carbon atom, which is the less substituted one. And this gets tautomerized, so this enol gets tautomerized to form the aldehyde, which is the final product. And again, the carbonyl group is bonded to the less substituted carbon, which is the terminal carbon. And here's practice problem number 14. Draw the products formed when the following alkynes are treated with each set of reagents. So for the first alkyne here, you can see that we have a terminal alkyne reacting with water in the presence of sulfuric acid and mercury sulfate as catalysts. And so that means is that the hydroxy group is going to be bonded to the more substituted carbon atom, so it's this one on the left, to form the enol, followed by tautomerization. So here's the formation of the enol. Again, the hydroxy group is bonded to the more substituted carbon atom, and then the hydrogen to the less substituted carbon. And again, the enol is not very stable, and so it gets tautomerized to form the ketone. And again, the ketone has the carbonyl group that's bonded to the more substituted carbon atom. And if we were to react this alkyne via hydroboration-oxidation reaction, the hydroxy group is going to be bonded to the terminal carbon atom, which is the less substituted carbon atom right here, to form the enol. And then it gets tautomerized into an aldehyde. All right, so here's the enol. So you can see, so the first step here is the formation of the borane, or the addition of the borane to the less substituted carbon atom. And this results in the formation of the enol after oxidation. And then this hydroxy group gets tautomerized into the aldehyde. And so the carbonyl group is bonded to the terminal carbon atom. And this is what we have as a final product. So this is the aldehyde. And for the second alkyne here, you can see that we have another terminal alkyne. And so reacting this with water in the presence of sulfuric acid and mercury salt as catalysts results in the formation of an enol in which the hydroxy group is bonded to the more substituted carbon atom, as shown here. So this is our enol. You can see that the hydroxy group is bonded to the more substituted carbon atom, and then the hydrogen to the less substituted carbon atom. And so this enol gets tautomerized to form the final product, which is a ketone. All right, and for the second reaction here, if we were to react this terminal alkyne via hydroboration-oxidation, we get this product right here, in which the borane is added to the less substituted carbon atom and the hydrogen to the more substituted carbon atom in an anti-Markovnikov fashion. And then we get the enol, in which the hydroxy group is bonded to the less substituted carbon, and this enol gets tautomerized into the final product, which is the aldehyde. And here's another practice problem. What alkyne yields each ketone as the only product both with acid-catalyzed hydration and after hydroboration-oxidation? So to answer this question, all you have to do is replace this carbonyl group with a triple bond, connecting this carbon atom with this adjacent carbon atom, as shown here. So you can see that we have an alkyne, an internal alkyne, which results in the formation of this molecule if you were to react this via acid-catalyzed hydration or hydroboration-oxidation reaction. And for the second part here, we'll do the same thing. And so we're going to replace this carbonyl group with a triple bond, which results in formation of an internal alkyne. So again, we would have the triple bond between these two internal carbon atoms, as shown here. So terminal alkynes are considered acidic because they contain an sp hybridized carbon to hydrogen bond. And so when they react with a strong base, this hydrogen atom gets deprotonated, which results in the formation of an acetylide anion. And this acetylide anion is considered a strong nucleophile capable of reacting with electrophiles like alkyl halides and epoxides. Since acetylide ions are considered strong nucleophiles, they react via SN2 mechanism. So here you can see that we have an acetylide ion reacting with an alkyl halide to form the alkyne. And so because acetylide ions are reacting via SN2, they react best with unhindered alkyl halides such as methyl halides and primary alkyl halides. So here you can see that, as I mentioned earlier, acetylide ions react best with methyl halides and primary alkyl halides. So here you can see that we have an acetylide ion acting as a nucleophile, attacking this electron-deficient carbon atom, which results in the cleavage of the sigma bond between the carbon and the chlorine atom, which results in the formation of a new carbon-carbon bond. And again, this undergoes via SN2 mechanism. When it comes to secondary and tertiary alkyl halides, however, acetylide ions undergo elimination reaction, more specifically E2 elimination reaction. So here you can see that we have an acetylide ion acting as a strong base, deprotonating this hydrogen atom. And so this results in the cleavage of this sigma bond between the hydrogen and the carbon atom, the formation of the pi bond, and the cleavage of the sigma bond between this carbon atom and the bromine atom. And so bromine is the leaving group. And what we have is a combination of products. We have the E2 elimination product and also the formation of the alkyne. So here's an example. Draw the organic products formed in each reaction. So for the first example here, you can see that we have an acetylide ion reacting with a primary alkyl halide. And so this ion here will act as a nucleophile attacking the electron-deficient carbon atom, which then results in the cleavage of the sigma bond between this carbon and the chlorine atom. And so what you have is the formation of this terminal alkyne and the chloride ion as the leaving group. And for the second example here, you can see that we have a secondary alkyl halide. And so what's going to happen is this ion will act as a base, as a strong base. And so it'll be able to deprotonate any one of these hydrogen atoms, which then results in the cleavage of this carbon to hydrogen bond and the formation of a double bond, and then the cleavage of the sigma bond between this carbon atom and the bromine atom. And so what we have is the formation of the product, the alkene here, cyclohexene, and the formation of the terminal alkyne and the bromide ion as the leaving group. So here's practice problem number 16. Draw the organic products formed in each reaction. So for the first one here, we have an acetylene reacting with sodium hydride and this alkyl chloride here. And so the first thing that you would want to do is react this alkyne with a sodium hydride. And so we're basically deprotonating this alkyne here. So that's the very first step, is generating the ion, the acetylide ion. So what we have is a acetylide ion here. And now this can react as a nucleophile attacking this electron-deficient carbon atom. And so this results in the cleavage of the sigma bond between this chlorine atom and the carbon atom, and then a carbon-carbon bond, sigma bond is formed. And so our final product is a terminal alkyne, and of course chloride as the leaving group. And then for the second reaction here, it's telling us to react it with an alkyl bromide. This is a primary alkyl halide and a tertiary alkyl halide. And so looking at the first one here, the reaction between this terminal alkyne and sodium hydride or sodium amide results in the formation of the ion, which then acts as a strong base this time. Or a nucleophile reacting with the primary alkyl halide here. And so again, the ion will attack this electron-deficient carbon atom, which results in the cleavage of the sigma bond and the formation of the final products. So we have the organic product here and also the bromide ion as the leaving group. Now reacting this ion with a tertiary alkyl chloride will result in this ion acting as a strong base, which can react with any of these hydrogen atoms here. These are the beta hydrogens. And so this results in the cleavage of the sigma bond between the hydrogen and the carbon atom, the formation of the pi bond, and the cleavage of the sigma bond between the carbon atom and the chlorine atom. And so what we have is the formation of the alkyne, the terminal alkyne, the alkene, and also the leaving group, which is the chloride ion. And so in summary, the first reaction undergoes SN2 mechanism, and then the second reaction undergoes E2 mechanism. And here's practice problem number 17. What acetylide anion and alkyl halide can be used to prepare each alkyne? Indicate all possibilities when more than one route will work. All right, so for the first alkyne here, you can see that we have a terminal alkyne. And so the first thing that I would want to do here is to label the two carbon atoms that form the new carbon-carbon bond. And so here are the two carbon atoms that basically act as a bridge, right? The new carbon-carbon bond. And so we're going to separate these two carbon atoms. And then the one on the left will be the alkyl halide, and the one on the right will be the acetylide anion. So here's the alkyl halide. So we have a primary alkyl halide. And again, you can use bromine atom, chlorine, or iodine. It doesn't really matter as long as we have a primary alkyl halide. And then if we were to react this with the acetylide ion, it will form this product right here. All right, and for the second one, we have an internal alkyne. And so what we're going to do is we're going to separate the two carbon atoms. So these are the two carbon atoms right here. And we're going to split them up. And the one on the left will be our source of acetylide anion, as shown here. And then on the right, we have the alkyl halide. And so an alkyl halide containing 1, 2, 3, 4 carbon atoms. And so here we have 1, 2, 3, 4 carbon atoms as well. A second possibility actually exists for this product. So if you were to label these two carbon atoms right here, then you can have an acetylide ion and also a methyl halide. And so if you have a methyl chloride, a methyl bromide reacting with a terminal alkyne, then you also get this product. So there are two possibilities here. All right, and for the third one here, we have another alkyl halide. However, the carbon on the left is bonded to a tertiary carbon atom, and the carbon on the right is bonded to a primary carbon atom. And so if we were to label these two carbon atoms right here, then you would have an alkene. Okay, and so as another product. And so the best acetylide ion and alkyl halide to use would be if we were to label these two carbon atoms right here and split them up, then we have this acetylide ion right here, and then the alkyl halide on the right hand side containing two carbon atoms. And so you can have an alkyl iodide or an alkyl bromide or an alkyl chloride. And so if you react these two together, what you get is this product right here. So in the next couple of slides, we're going to look at reactions involving acetylene and acetylide ions. So we know that an acetylene molecule has two sp hybridized carbon to hydrogen bonds. So that means that these two hydrogen atoms can be deprotonated by two equivalents of a strong base. And so it can undergo two sequential reactions in order to form two new carbon-carbon bonds. So here's an example. Identify the terminal alkyne A and the internal alkyne B in the following reaction sequence. So here you can see that we have an acetylene molecule reacting with a strong base. And this results in the formation of an acetylide ion reacting with an alkyl bromide. And this reaction results in the formation of an alkyne, a terminal alkyne labeled A. And this alkyne will react with another equivalent of a strong base, followed by a reaction with an alkyl chloride, resulting in the formation of an internal alkyne labeled B. So let's take a look. So here's our acetylene molecule reacting with a strong base. So this hydrogen here gets deprotonated, which results in the cleavage of this bond between the carbon and the hydrogen and the formation of the acetylide ion. And this acetylide ion reacts with the alkyl bromide. And so this acetylide ion will act as a strong nucleophile, attacking this electron-deficient carbon atom that's bonded to the bromine atom. And so this sigma bond breaks, which results in formation of a terminal alkyne labeled A, as shown here. So now this terminal alkyne can react with another equivalent of the strong base because it contains one more hydrogen. So we can deprotonate this second hydrogen here using another equivalent of the strong base. And this forms the acetylide ion, which can act as a nucleophile. And this reacts with the alkyl chloride, and it will attack this electron-deficient carbon right here, cleaving this sigma bond between the carbon and the chlorine atom, which results in the formation of the final product, which is an internal alkyne. Here's practice problem number 18. Show how acetylene, ethyl bromide, and 1-bromo-3-methylbutane can be used to prepare 7-methyl-oct-3-ine. Show all reagents and use curved arrows to show movement of electron pairs. So here we have acetylene reacting with a strong base. And so this first step deprotonates this hydrogen atom right here, which results in formation of our first acetylide ion. And this acetylide ion then reacts with ethyl bromide. And so it attacks this electron-deficient carbon atom right here, which results in the cleavage of the sigma bond between the carbon and the bromine atom. And this results in the formation of a terminal alkyne. And you can see that this contains another hydrogen atom, which can be deprotonated. So we can use another equivalent of a strong base. And this deprotonates this hydrogen atom, resulting in the formation of the second acetylide ion. And this ion, acting as a nucleophile, will react with 1-bromo-3-methylbutane. And so it will attack this electron-deficient carbon, resulting in the cleavage of the sigma bond between this carbon and the bromine atom. And this results in formation of the final product, which is 7-methyl-oct-3-ine. So acetylide ions can also react with epoxides via SN2 mechanism. So here you can see that we have an acetylide ion attacking this less substituted carbon, which opens up the ring. And this results in the formation of this structure with a negative charge on the oxygen atom. Reacting this with water results in the protonation of this oxygen and forms the alcohol. And here's another example. We have an epoxy cyclohexane reacting with an acetylide ion and water to form a pair of enantiomers. So you can see that this acetylide ion can attack on either side of the epoxide. It can attack this top carbon or this bottom carbon. And this results in the formation of racemic mixture, a pair of enantiomers. Here's practice problem number 19. Draw the products of each reaction. So here you can see that we have an unsymmetrical epoxide. And so that means that this acetylide ion acting as a nucleophile via SN2 mechanism will attack this less substituted carbon atom, as shown here. And so what happens is it opens up this ring, which results in formation of the product. So when you react this with water, you have the triple bond bonded to this carbon at the bottom. And so you have, since this is a backside attack, the orientation is going to be facing towards the back, and then the alcohol, the hydroxy group, is facing towards the front. And then for the second reaction here, we have a symmetrical epoxide. So that means that this acetylide ion will attack on either side of the epoxide ring. And so when that happens, we have a pair of enantiomers that will form. So it can attack the top carbon or the bottom carbon. And so if the acetylide ion attacks the top carbon, then it results in formation of this product here. And so the triple bond is going to be bonded at the top carbon and then the hydroxy group at the bottom carbon. However, if the acetylide ion attacks the bottom carbon, then we will have this structure here in which the triple bond is connected to the bottom carbon and then the hydroxy group to the top carbon. And so we have a pair of enantiomers, which is a racemic mixture.